Greetings, math people. It's Mr. Ray here. With our next lesson in grade 11 University Math, we are working in the trigonometry unit. And today we're going to talk about the unit circle, which is a very important tool to be able to calculate sine, cos, and tan ratios for all sorts of angles. So we're going to go through this hopefully slowly and carefully. You need to have done the previous lesson where we talked about special triangles, and in that lesson we learned, here's our two special triangles here. We have our 30, 60, 90 triangle, named that because of the three angles inside. We also have a 45, 45, 90 for the same reason. And in the previous lesson we were able to get the exact side lengths that would be required to make such a triangle with these angles inside. So the 30, 60, 90 triangle had a hypotenuse of 2, and the other two sides were 1 and root 3. Notice we're not putting that into a calculator because root 3 is, call it an irrational number. It can't be written as a fraction or a decimal unless you round it, which we don't want to do. So we leave it as root 3, and that'll make all our trig ratios that we calculate today. It's going to make them exactly correct, not approximately correct. Our second triangle we came up with, this is basically an isosceles triangle. So these two sides are equal. We gave them a side length of 1, calculated the hypotenuse to be root 2 using Pythagorean theorem. So we are going to use these two triangles today. But before we actually use them, we're going to be creating something called a unit circle. Now, everybody knows what a circle is. A unit circle means a circle that has a radius of 1 unit for 1. Before we can actually put these inside the unit circle, I actually have to make the hypotenuse equal to 1. And that's because the hypotenuse will be, when we put on the unit circle, the hypotenuse will be the radius of the circle. You'll see that once we do it, but for now let's just take my word for it. So I'm going to create, we're going to create similar triangles meaning same angles inside, same shape, but different side lengths. I want to change the hypotenuse here to a 1, which means if I divide all three sides by 2, I will accomplish that goal. So if I do that, I'll get this triangle down here. 2 divided by 2 is 1, root 3 divided by 2 is root 3 over 2, and 1 divided by 2 is 1/2. So here's our shiny new triangle, 30, 60, 90 triangle. Now you can see 30, 60, 90 has two angles that we're going to use, 30 and 60. So I've just created kind of a reoriented version of this triangle. This version I've got 30 degrees in the bottom left. Here I have 60 degrees. It's really the same triangles, just kind of flipped over and turned. You can hopefully see that. Okay, and then this second special triangle, 45, 45, 90, I want to make this side equal to 1, so I'm going to divide both sides by root 2. When I do that, I get this triangle here with my goal of having the hypotenuse 1 and 45, 45. These two sides are going to be 1 over root 2. Now 1 over root 2 is actually the same as root 2 over 2. So, and the way they're similar is if I multiply the top and bottom by root 2, I get this version of it. So in your math journeys on the internet, you'll probably see a lot of references to these sides being not 1 over root 2, but root 2 over 2. Just keep in mind they're the exact same value. It's just math people don't like to have roots on the bottom, on the denominator. We like to rationalize the denominator, turn it into an integer, so that's why you'll see that a lot. Personally, I'm okay with either one. If you use 1 over root 2, great. If you use root 2 over 2, that's great too. So whatever you prefer to use. Okay, so let's start with the unit circle. So the unit circle, we're actually going to kind of put this on an XY plane. Okay, center of the circle will be at the origin of the XY plane, 0.00, and the radius of the circle will be 1. Okay, so these aren't really 1. This is like, I don't know what it is, 1/8 or something. So this will be, let me just maybe further label this. So this is the x-axis. This is the y-axis. Okay, just to make sure you're oriented correctly. And I just kind of drew a circle with a radius of 1 around from the origin. So we can actually put some points on here, because if I know the radius is 1, okay, that point would have an x-coordinate of 1, y-coordinate of 0. So I have a point on my unit circle. I could also go 1 this way. So the x value now is -1. Y value is still 0, or I could go up 1. So just remember, we've got a radius equal to 1 all the way around. So this point would be 0, 1, and this would be 0, -1. So we've got 4 points on our unit circle. The goal will be to create, we're actually going to create 12 other points around here using trigonometry, and it's going to be very useful. Okay, now just a little bit of terminology in case you're not sure. Now that we're using this Cartesian plane, the XY plane, sometimes we talk about quadrants. A quadrant is one of 4 regions. Okay, so you can easily see if I make this XY grid, I've got 4 quadrants. So you'll see that we name these. We start in this upper right quadrant. We call that quadrant 1, and then we go counterclockwise to name the rest: quadrant 2, quadrant 3, and quadrant 4. Okay. Now what we're going to be doing on the next page is we're going to be, for example, I can now create an accurately scaled version of this, and I can put it on inside the unit circle here, so that that point there is at the origin, and this radius, the hypotenuse, will go out and meet the outside circle there. So that's what we're going to be doing, and I can do that with all 3 of these. I can put this bottom side of the triangle along the positive x-axis, and you know, as long as that left corner is pointed here, the top corners of all 3 triangles will end up intersecting the circle, the outside of the circle. Okay, so it's kind of like angles in standard position that we learned in the last lesson. We basically put our initial arm along the positive x-axis, and the terminal arm is the sort of the other side of our angle that makes the 60, the 30, or the 45. So that would be the terminal arm, the initial arm, and in order to get the angle, we move counterclockwise from the initial arm to the terminal arm. So this was stuff we did in the previous lesson. So that's kind of why we learned it, because we're basically putting these angles in standard position, at least for now. Okay, so let's move to the next page, and you see this glorious diagram, which is the unit circle. So let's zoom in a little bit. Okay, so we're actually going to create this ourselves, and the goal would be that I should be able to give you one of these blank unit circles in a few days from now, and you would be able to actually fill it in. Okay, and the only thing you really need to remember is these, well, the 2 special triangles, or the 3 if you consider these 2 as separate, but they're really the same. Okay, so the first thing we're going to do is we're going to actually put the angle in. So if you think about this as the XY grid. It still is an XY grid. We just haven't put the axes labeled here, but it is. So an angle of 0 would be where the initial arm starts. So the initial arm starts here. If I go 0 degrees from there, that would be an angle of 0. Okay. So I'm going to go around the circle here, and you can see inside the circle, we've got this little, that's a degree symbol there. So this is where I'm going to put the degrees, and there's actually 2 listed here. So I'm going to start here with 0. So that's 0 degrees. We'll see what that becomes. It actually has a value. And if I just do the ones that I know right away, so I know if I go 90 degrees, this angle would be 90, so I'm going to put my 90 degrees here. If I go another 90 degrees, that's 180. Another 90 degrees, that's 270. And if I go back to where I started, well, that's another 90, so that's 360. So 0 and 360 degrees are the same terminal arm. In other words, these are coterminal angles. We talked about that last lesson as well. Okay, so let's start filling in some of these other angles. And these are going to be based on the 30, 60, 90 and the 45, 45. So we have 3 angles between 0 and 90. So guess what they are? Well, they're 30, 45, and 60. So these have been strategically placed, so they're accurate. So this will be 30 degrees, this will be 45, and this will be 60 degrees. Okay, well, what happens as we go around here? So I find the easiest way is to think in terms of multiples. So if I just started with multiples of 30, okay, I can see it, well, 0 times 30 is 0, 1 times 30 is 30, add another 30, 60, 90, another 30 would be 120, so that would be here. Another 30 takes us here, 150. So we're skipping by these ones these are going to be multiples of 45. We'll do those at the end. 150, 180, keep adding 30 degrees, 210, skip that one, 240, 270, 300, 330, and then we're back at 360, which is another multiple of 30. Okay, so the only thing left are these 3 angles here. These are all multiples of 45. So if I think about multiples of 45, well, 0 times 45, 1 times 45, 2 times 45. If I add another 45, that's over here. 90 plus 45 is 135. Another 45 takes us to 180. Another 45 takes us to 225. Another 45 takes us to 270. Another 45 takes us to 315. So we've completed all the angles around the unit circle. Multiples of 30 degrees and 45. That's a nice way to think about it. Okay, so we're ready to start. Well, actually, there's one more thing we can do. And if you remember from the previous page, we actually knew 4 points around the unit circle. That would be at 0 degrees, 90, 180, and 270. So based on the X and Y position, if I'm putting the coordinates of this point, okay, I know this has coordinates 1, 0. So that's supposed to be a comma there. This would have negative 1, 0. This would have 0, 1. This would be 0, negative 1. Okay, so now our goal is to figure out what the coordinates are for these other angles. Okay, and they're not obvious like the 0s and 1s and negative 1s are. They're not going to have really nice numbers, at least most of them won't. So this is where we bring in our special triangles. So I'm going to start with the 30-degree measurement. So if you, I don't know if I can show this. So I've got my 30-degree triangle here. So that, just imagine I'm picking this up and actually placing it inside here. This is a 30-degree angle right there. And this has a hypotenuse of 1, which coincides nicely with this radius of 1. So I can kind of imagine if I dropped a perpendicular line down there, I would have this exact 30, 60, 90 triangle. So that's got length 1. This would be along here to this point would be root 3 over 2, and this length would be 1/2. Now, if I'm thinking about the x and y coordinates at this specific point here, well, I can get those from the triangle because I know the length from there to there is my x coordinate because it goes straight up there. And I happen to know that's the side length of this triangle, which is root 3 over 2. So I can now fill in my first real coordinate. So the x coordinate for this point will be this side here. So that's root 3 over 2. Okay, and then the y coordinate, if you think about this side, this is the distance from the x-axis up to the point, and that's exactly what the y-coordinate is. So that is the side over here, the vertical side. So that 1/2 is my y-coordinate of that point. Okay, so hopefully that makes sense. If I do, let's see if I can do this. If I look at my 45 triangle, so I'm now focusing on this angle here. So if I drop a perpendicular down here, okay, that, well, it's actually this angle here I'm looking at. That's a 45-degree angle. That's a 90-degree angle, so that makes that 45 as well up there. But in terms of these side lengths, we already know the horizontal side is 1 over root 2, the vertical side is 1 over root 2, and this corresponds to my x-coordinate because that's how far to the right I'm going. So the x-coordinate here, 1 over root 2, and the y-coordinate, how far up or down did I go along here? Well, that's that side length, which is also 1 over root 2. Okay, so we've got our second point. And then the third point is using this triangle. Right, this is the taller triangle because the 60-degree angle in the corner. So again, if I drop a perpendicular down here, well, there's my special triangle right there. 60 down here, 30 up here, 90 here. So again, if I want to know these coordinates, I'm just looking at this triangle. This will be my x-coordinate horizontally. This will be my y-coordinate, this side. So this will be the x-coordinate is 1/2 because that's the bottom side of that triangle. Coincides with that x value there. And the y value is root 3 over 2. Great. Okay, so I've used those all three of those triangles, and I've completed all three sets of these coordinates here. So does that mean I've got to do this all over again over here and over here and over here? No, we're going to use symmetry now to complete the rest of the unit circle. So I'm going to go over, so remember this is quadrant 1, this is quadrant 2, quadrant 3, quadrant 4. Okay, if I go over to quadrant 2, this arc over here, I can think about some similarities here. So if I'm comparing this point here, which I know, to this point over here, and I ask myself, what do these 2 points have in common? I can see, well, they're going to have the same y-coordinate, okay, because it's the same height as over here. So I can basically copy the value that I've already got for this point here. So I know the y-coordinate is root 3 over 2. And I can do the same for this. The 45 reflects over to the 135 angle. And I know the y-coordinate is also the same. So that's 1 over root 2. And this 30 degrees reflects over to the 150 point. So the y-coordinate there is 1/2. That's the same over here. So I can put that in as well. Now, what about comparing the x-coordinates between here and here? You can see that I've reflected this point across the y-axis. And that means that basically the x-coordinate will be the negative version. Sorry, this x-coordinate will be the negative version of this value because it's, instead of being 1/2 units to the right, it's 1/2 units to the left. So these values over here for the x-coordinates will be the negative versions of these x-coordinates. So I'm just going to fill all of those in. -1/√2 from the 45 to 135, and -√3/2 for the 150. Okay, so that was a lot quicker. We used the property of symmetry to get these values. You can see the y coordinates here are the same as the y coordinates here as we go across, but the x coordinates are the negative versions. Okay, now let's go down to quadrant 4. So again, I could look at, this point here to this point here. Okay, what do these 2 points have in common? Well, they're going to have the same x coordinate because it's the same distance to the right. So whatever that x coordinate is there is also down here. So this is √3/2. Okay, and same thing with this. This reflects down here. This is 1/√2, and this is 1/2. Okay, now what about the y coordinates now? So if I compare this point to this point, the y values, well, this goes up 1/2 unit, but this goes down 1/2 unit. So this y coordinate would be the negative version of this, so -1/2. Similarly, this will be -1/√2, and the last one -√3/2. Okay, notice I'm not doing any memorizing here. I'm just using properties of symmetry to get the rest of the points. So the only points I really had to get were these 3 here. Now, what about this quadrant here, quadrant 3? Well, I could do this in one of 2 ways. I could think about, well, I could start with these points and see how they compare to these downwards. Okay, or I could look at these points here and see how these points reflect over here. Either way you do it, you're going to get the same coordinates. Now, think about the XY grid, okay, in terms of the signs of the coordinates. So in quadrant 1, the X and the Y coordinates up here are both positive. Over here, the Y coordinates are positive, but the X coordinates are negative. Down here, X coordinates are positive, Y coordinates are negative. And down here, X and Y are both negative. Okay, so basically if I took this point and reflected it down here, like there, it's the same point, but this time the y value is negative. So this point here will have same x coordinate, -√3/2, but the negative of the 1/2. So all of these points will have negative x and y coordinates. So this one would be -1/√2, -1/√2. Hopefully that makes sense with the grid, just thinking it as it like a Cartesian xy plane. Okay, and the very last point, same x value, -1/2, and the negative of the y coordinate here, so that's -√3/2. Okay, we've completed our unit circle, so congratulations. Hopefully that made sense. Think about whether you could create that by yourself. If you could just come up with these 3. Let me zoom back in a bit. Sorry. Okay, if you could create these 3 special triangles, or 2, you should be able to come up with this diagram. Now, you're probably thinking, okay, we did the unit circle. What's the big deal? Like, what are we using this for? Okay, so what we're going to be able to do. So I'll tell you up front, and then I'll show you how we do it. We already knew from what we did in lesson 1, we could get the cosine, sine, and tan ratios for these 3 angles, for 30, 45, and 60. So we knew how to get those. With this, with the unit circle now, we'll be able to get the sine, cosine, and tan ratios for all of these angles. So from 0 degrees to 360, multiples of 30 and 45, we could actually come up with, say, example, if I asked you what the, what's the sine of 210 degrees, okay? I won't say what it is, I'll show you that in a second, but you'll be able to do that just by looking at this chart, okay? So that's a pretty powerful tool. So how do we get there? We're going to start with, we'll start with SOHCAHTOA, okay? So from SOHCAHTOA, you know that sine theta equals opposite over hypotenuse. We know that cosine theta is adjacent over hypotenuse, and tan theta is opposite over adjacent. So these are straight from SOHCAHTOA. We're going to update these now. So if I looked at, let's just focus on this one triangle here. So this 30-degree triangle here, the first one we did. So there's my reference angle down in this standard position here. So if that's my reference angle, that makes this side here is hypotenuse, this side here is opposite, and this side here is adjacent. Okay? Now, we're going to actually convert these to, instead of these names, into the sides of these triangles. What do they actually represent? So if I'm looking at this triangle again, I know that the hypotenuse is actually the radius. Okay, so I'm going to change hypotenuse to radius. Okay, and I know in this particular case that radius is always 1, but we'll just call it r for now. If I looked at, so back to this triangle here, the opposite side is this side of the triangle, and we knew from what we did in the unit circle that this side here represents the y value. Okay, so opposite equals y. And finally, the adjacent side here down here, that represents the x value, the x coordinate. So adjacent equals x. So if I just do that conversion, sorry, I wasn't in focus there. So I'm going to change hypotenuse to radius, opposite to y, adjacent to x. When I do that, you can see I get these new versions of SOHCAHTOA for the unit circle. So sine is y over r. Sine theta is y over r. Cos theta is x over r. And tan theta is y over x. Okay, now there's a relationship between x, y, and r because these are all basically right triangles. So I could use my Pythagorean theorem. I can figure out that the radius is equal to, well, starting off with r squared equals x squared plus y squared. I could take the square root of both sides and get that r is the square root of x squared plus y squared. That might be handy later, but just that's defining what r is. R is the radius, which is equal to 1 in our case. And that's exactly what we do down here. Since we know that r value is 1, if we update these formulas, sine theta equals y over r, well, that's r is 1, so sine theta is just y. Cos theta equals x over r is just 1, so cos theta equals x. And, well, we don't have an r in the tan formula, but so we write it as y over x. But we already know that based on what we just did above, y is sine theta and x is cos theta. So here is our first identity, which we'll be using at the end of this unit. Tan theta is actually, this can be written as sine theta over cos theta. Okay, you can still think of it as y over x, no problem, but eventually you'll be thinking in terms of sine and cos instead of y and x. Okay, so these are very important now because, and this will be your homework today. So let's do an example of this. So if I've got my unit circle here, and say I asked, let's just repeat the formulas up here. So sine theta equals y, cos theta equals x, and tan theta equals y over x. Okay, so if say I gave you the question, I want the three trig ratios, sine, cos, and tan, for the angle 210. So I can see that sine of 210, how do I get that? Well, I go to the point on the unit circle for the angle of 210, and I know that the sine value will be the y coordinate of this point. So the y coordinate of this point is -1/2, so that's what sine of 210 is. So I take that answer back here from the unit circle, and I know that sine 210 is 1/2, -1/2. You can try that out in your calculator, you'll see that it's true. Then we'll do cosine of 210. Cosine of 210 is the x-coordinate. So the x-coordinate at that point at 210 degrees is -√3/2. Okay, so we got 2 of the 3 so far. The third one, tan of 210. This one's a little trickier because unlike sine and cos, I can't just look at the picture, the unit circle, and grab the value, grab my answer. It's the ratio of the y and the x. So if you think about it, it's y over x, which I already know here, but if I go back here, y is -1/2 and x is -√3/2. Now, so when you're doing this, think about it as a fraction dividing by a fraction. So we're going to change that into a fraction times the reciprocal of the bottom. So if I flip that upside down, I'll keep my negative sign on the top, so that's 2 over √3. This is a lot easier to work with. I can actually cancel the 2 there with the 2 there, but I still have a negative there. So if I multiply across here, I get, so that's going to be a positive, -1 times -1. So +1 over, that's gone, so it's just √3. So I was able to get all 3 trig ratios for that angle of 210. I can do that exact same process for all these other angles from 0 back to 360. Okay, so that's the power of the unit circle, and you're going to be relying on that not just in grade 11 but grade 12 as well. Speaking of grade 12, if you notice there's a couple of lines here that we didn't fill in, and that's because this will be used in grade 12. This is where I mentioned before, when you measure angles, it could be in different units. It can be degrees, radians, or gradients. The radians we'll use in grade 12, so that's what these places are for, will be those angles in a different unit. So leave those blank for now, but you'll see those in grade 12. Okay, just a couple other things here. We have something called the cast rule. And again, we had, if you relate, so there's our XY grid again, okay, and our unit circle. So remember, we call these quadrant 1, quadrant 2, quadrant 3, quadrant 4. Well, if we apply this cast name, so the numbering is a little different than the quadrants. We start down here in the bottom right, not the top right, and then go counterclockwise for the word cast. Okay, so what does that stand for? Well, maybe you recognize S, T, and C. That, those are our trig ratios: sine, tan, and cosine. And this actually stands for all. So the cast rule actually tells you what will the sign of the different ratios be in each of these quadrants. So for example, for the C, in this quadrant here, cosine is the only positive ratio. So all cosine values here will be positive. Sine and tangent values will be negative. Okay. In the A quadrant, or quadrant 1, all 3, sine, cosine, and tan ratios will all be positive here. Here in the second quadrant, only sine is positive, cosine and tan are negative, and down here, quadrant 3, where the t is, that says that only tangent ratios are positive, cosine and sine are negative. Okay, and that still relates, cosine and sine relate to x and y. Sine's positive up here because it's the y value. Sine's negative down here. Cosine's positive here because it's x value. Cosine's negative over here. Tan's a little bit different because it's a ratio of the x and the y. So if you think if x and y are negative, negative divided by negative will be positive. So that's why tan is positive here. Okay, so that's usually helpful. Couple more things here. For any given cosine ratio, so for example, if I said, if I have a cosine ratio of root 3 over 2, there will be exactly two distinct angles that have that cosine ratio. So if I go back to my chart, so remember I'm looking for a cosine ratio of root 3 over 2. So cosine will be the first coordinate, the x. So if I'm looking for root 3 over 2 in the x coordinate, I've got one here at 330 degrees, and I have another one here at 330. So you can see there's two angles, 30 and 330 degrees, that have a cosine ratio of root 3 over 2, and that's going to apply for any of these values. Okay. Same thing applies for the sine ratio. If I said, if I'm looking for a sine ratio of, say, -1/2, okay, if I go back to my, so I know sine's positive up here, so -1/2 I see right here at 330 degrees, and I also see over here at 210. So the two angles, 210 degrees and 330 degrees, both have a sine ratio of -1/2. And then the tangent's kind of weird. It's a little bit harder to find the matching angle. You actually look at across. So for example, if I'm looking for a tangent ratio of 1, well, I have to do that calculation here. So I can see a tangent ratio of 1 happens when the x and y coordinates are the same. So I can see that's going to happen here. So 45 degrees has a tangent ratio of 1, and the other place that will have it will be directly across the circle at 225, because those two values are -1 over root 2 each. If I divide those, I get 1. So the matching tan angle that has the same tangent ratio will be exactly 180 degrees across the circle. Okay. Yeah, and there's a little reference here to coterminal angles. We'll talk more about that in a subsequent lesson. So the homework here that I've assigned for you is to basically make a chart. So down the left part of your page, you'll create all of these angles from 0 to 360, and then I want you to calculate the sine ratio in one column, cosine ratio, and tangent ratio for all of those angles. So it'll be using what we just created here. So I don't want you to be using a calculator for this, because I'm asking for exact ratios, which the calculator won't give you. I want you to use this exercise to be able to use the unit circle to get those sine, cosine, and tan values or ratios. Okay, so that's it for today. Very important lesson. Hopefully it made sense. And we'll continue on with looking at some other more minor parts of trigonometry. But the part that we learned today and on the last lesson, very important going forward that you understand these concepts. Okay, so thanks for joining me today, and we'll see you on the next lesson.